Hello, everyone. We starting our session of electronics. Today we will have 6 presentations. All presenters are here. And first, I would like to inform how we are going to work. For every presenter, 15 minutes are dedicated. And let's say 10-12 minutes for presentation and 5 or 3 minutes for questions and discussion. Let's keep that schedule, but it's not very strict. Now we start from one more information. You should switch your camera on when you are presenting, and the other presenters can be with cameras on or can be off, but the microphones must be muted. Okay, now we start from presenter from Czech Republic, Roman Sotner. He will make presentation on topic integer and fractional order VCO using non-internal amplitude stabilization and modern active elements. So the floor is yours, please.
Hello, everyone. Thank you for my introduction. I will present contribution entitled integer and fractional order voltage controllable oscillator using non-inertial amplitude stabilization and modern active elements. My name is Roman Sotner. I am from Brno University of Technology. We are closely cooperate with King Mount Goods Institute for Technology in Thailand with some guys. So our goals today are following. We are several.
Roman, you should share your screen.
Yeah, I forgot. So we have a few points to discuss. First point covers some motivation to this topic. There will be defined, I think, 3 goals which are necessary for our design. Then I show the proposed circuitry, and circuitry of the oscillator will be tested with integer order elements and also with fractional order elements. We will see some consequences and some theoretical aspects of this work. So there are many active devices. Unfortunately, most of them are not commercially available. We were focused in the research on the special active devices that are available commercially in the shops, because no many colleagues has availability to some integrated circuits technology or fabrication process and so on. Therefore, we select this way of the design in this contribution. Despite that, there also exist some very useful devices which can offer simplification of topology and some electronically adjustable features. In our work, we are targeting on the adjustable gain of these devices, which is typically below 1. We are not using variable gain amplifiers that reach adjustability range of the gain from 10 up to 100 and so on. It is not necessary in such design. And some interesting conclusion is from the integer order elements used in design, because integer order elements means that the distance between generated phase shifts is always integer multiple of 90 degree. On the other hand, in fractional order elements, the design always offers some arbitrarity between the generated waves, because there are available multiples of some non-integer phase shift between waveforms between 0 and 90 degrees in theory. So our goals of the design are targeting on the simple structure which is using integer and also fractional order elements, and where we are concentrating on the special parameter or special feature of this topology, where we are targeting on only a single time constant, which is used for the tunability of oscillating frequency. As I discussed, we are targeting on implementation of commercially available parts, because they are simply available for workers. And the most important goal of our work is the analysis of design equation, because there is a little or more significant difference between standard integer order approach, and also you can see that some boundaries between conditional oscillation and also frequency of oscillation are disrupted here. Our proposed topology has typical block concept, because we are using lossy integrator, lossless integrator, and the feedback loop is used for the amplification or limitation of the signal. This loop is responsible for control of conditional oscillation. In our design, this is gain which is given by a ratio of some resistors. As you can see, the complete circuit topology, this is a really working circuit topology with specific active devices used, two multipliers, two voltage multipliers that are used for amplification of the gain in the loop. They are based on multipliers, which some standard transfer equation. Most typical for these multipliers in this configuration is that the range of the available gain is between 0.1 and 1. The rest of parts are a differential voltage buffer and so-called diamond transistor. We can imagine the diamond transistor is some kind of operational transconductance amplifier or current conveyor. It is nothing spectacular. The most interesting for us that is this transfer of the integrator, this lossless integrator, because we can see that all controllable parameters are there are two gains here are targeting to these blocks. In standard cases, the tunability is targeting to both integrators, also to tau2, but not in our case. That is a little bit different from previous works. We selected our design specification to some quite high frequency range for these devices between 0.6 and 6 megahertz, because this is all of, we calculated that this is valid for these selections of passive elements, capacitors 150 picofarads and resistances 180 ohms. And for this available range of gain, to gain, as is clear from this equation, is directly given by a DC control voltage DC component. So the stabilizing part for the inertial settings includes these value of resistances, but the R4 should be in the precise designed adjustable trimmer, which is initially setting start up of oscillation and will be working. The characteristic equation of this oscillator has the typical form. We can see that both gains, if they are equal, allow of linear control of oscillating frequency. The condition, as is clear from previous picture, respects that R4 must be equal or a little bit higher than R3. And this is also a very important analysis for us, because it shows us a relation between produced output waveforms. You can see that there are always equal amplitude, because gains are same, resistances are selected as same, and the capacitors too. And minus J means that there is 90-degree phase shift, as the typical for quadrituple oscillators. There are some typical results. We are changing driving voltage from 0.1 to 1, and the frequency is changing between 0.8 megahertz up to, I think, 6.3 megahertz. The variation of output levels is between 0.2 and 0.4. We can see that in the part of bandwidth where the parasitic influences are not so effective, are really identical output levels. It is peak-to-peak value. Total harmonic distortion was analyzed for full range of the adjustability. We can see that in most of the range there is THD in the range between 1 or 1 and 2%, and produced phase shift is a little bit changing the value from 90 to 95, 96 degree. This Sparse is I think a little bit influenced by parasitic influences and finite bandwidth of used active devices. There are typical examples of the output spectral analysis. We can see that suppression to higher harmonic component is more than 40 dB. It really corresponds with these results in the middle of the bandwidth somewhere. This is test for example of this analysis for some specific tone. We are using also in our second part of this work so-called constant phase elements. These elements are known as fractional order devices of some fractional order capacitors. We are simply replacing C1 and C2 in our topology with impedance, which has character of fractional order capacity with order 0.5, and this is called equivalent capacity or pseudo capacitance. It is a little bit high value, 56 microfarads. Therefore, also application range of this device in the application in the circuit will be a little bit lower. We are showing results in magnitude and into phase. You can see that operation bandwidth is essentially between 100 Hz and 100 kHz, and expected phase ripple in this bandwidth is ±4 degrees. The design of elements is a little bit boring procedure for the MATLAB or some tools, and there are many papers dealing with correct selection or correct design of values of passive elements. If we are applying the fractional order devices in our oscillator for the same values of the rest of the parts in this topology, and also for identical value of gains used for tuning, and we select due to limitation of the device of the constant phase element due to low impedance value here, new oscillation frequency. For this frequency, it was necessary to calculate new values of the gain and also new value of the resistor R4, because this resistor is responsible for fulfillment of conditional oscillations. As we can see from a new characteristic equation and deep analysis of this equation, the new condition has form which is also dependent on omega. It means that a condition is dependent on frequency. It is not very beneficial feature. However, if we are applying automatic gain controlled circuit, which is which has possibility to compensate the gain in the feedback loop here. Now it is determined by a resistance ratio, but in some cases we can use, instead of this block, also some variable gain amplifier and so on, as we show also in our next work. That compensation doesn't have effect on the frequency, and oscillator is working in some range of the tunability. Again, frequency is also given by a variable gain A, but unfortunately there is this relation between condition. As we can see from analysis of the transfer between voltage across the capacities, there is really phase shift dependent on the order. It means that if we are selecting order of the fractional order device, then we are selecting also available phase shift between waveforms. In our case, the experimental results measured by oscilloscope yield this value of frequency. There is, I think, 15% of deviation, and phase shift 46 degree. Phase shift is fitting best our expectations. In this case, we were not used automatic gain control circuit into feedback loop for conditional oscillation control. It was inertial. It was non-inertial part based on diodes. But we also, in our next work, which is not detailed described here, also used into feedback automatic gain control circuit, and there are results. You can see that we are always keeping in some bandwidth constant phase shift. There is not 45, but minus 135, because this is a little bit different oscillating structure. But we can see that in some limited bandwidth, we obtained constant phase shift between output waveforms for also different orders. I have to note that orders of the constant phase device are always influence the range of the frequency. You can see that for very low range, for very low order, 0.25, the range of the adjustability is a little bit higher than in previous cases. So I have to conclude these results. So we present some topology that is very useful for traditional integer order designs, but in the fractional order implementations and implementations of fractional order devices, there are some limitations that we clarified in this contribution. Two amplifiers based on the adjustable gains are used in the lossless integrator only, in the part of the lossless integrator, and it has not principal effect on generated signals. As we saw in the analysis, there is not amplitude phase shift variation in the ratio. So it means that phase shift is keeping constant, and also amplitude of produced amplitude is keeping constant during the tuning process. And the most important conclusion is that in fractional order implementation, this kind of oscillator has to be always used with some amplitude gain control circuitry. Without this blocks, it is not able to operate, and we have to set for each selected oscillation frequency the gain required for fulfillment of conditional oscillation. So thank you for your attention.
Thank you for your presentation. Does anyone have any questions? Okay, then I will ask. Could you open slide number 7?
Slide number 7, yes, here.
But you should share your screen.
Yeah.
So at harmonic distortion values, we see that at 3 megahertz, we have the lowest value. Could you explain how it's happened?
I think it depends on the gain variation in the structure, because in the operation of these devices, the range of units of megahertz is at the border of the usability, because it requires precise design of PCB and so on. So the most important thing is that this it is not dependent. Therefore, there are not connected points. It cannot be supposed or understood as a dependence. It is given by some non-linearities in active circuits and transfer response of active circuits. Typical for devices which are used in our design is that their own suppression of higher harmonic components is, I think, only 40 or 50 dBc. So therefore, we have this value of frequency. But the consequence that there is only at about 3 megahertz, the lowest value, there is nothing like rule. It is nothing given by some dependence or some theory.
Okay, thanks. And could you point out some weaknesses of your solution?
Yeah, as I discussed, the weakness is frequency limitation of the devices, because it will be beneficially working with some kilohertz, 10 of kilohertz frequencies bandwidth, but above, I think, 10 megahertz, there are issues with frequency bandwidth limitation of active devices. And also, as we saw, that the inertiality of the feedback amplitude limitation, we used some standard diodes. It's not very good idea, because we have to use better types of diodes, and it always limits also available ranges of amplitudes. And I think the last negative point is that, but I don't know if we want to understand it as like drawbacks, because we find it now, because we don't know. There are aspects were not very significantly studied in the previous works. So it is application for fractional order operation. It is a little bit complicated, and it has many further questions than standard integer order designs.
Okay, thanks.
You're welcome.
Any more questions? Okay, thank you for your presentation.
You're welcome.
And the next presentation comes from Serbia, presenter Vranjkovic. And the topic is hardware acceleration of sparse support vector machines for edge computing.
Can you hear me?
Yes.
Okay.
Yes.
I'm Vranjkovic. I'm in front of authors Rastislav, Struharik, and myself. In this paper, we present one hardware accelerator for support vector machine, which can use sparse attributes of input instance. This is a brief overview of presentation. I will shortly introduce support vector machine. I will give motivation for sparse support vector machine. I will say which algorithm we use to give a sparse support vector machine from regular support vector machines. Then I say something about architecture, which can take advantage of sparsity, and at the end I will show experimental results of this work. So support vector machines were the most popular machine learning algorithm before convolutional neural networks appeared. They are a supervised learning algorithm. That means that there are two phases. One is a learning phase, and then there is a predicting phase. For learning phase, we need input data to train the machine, and then machine can predict outputs on the new input instance. On the picture right, you can see the main idea behind support vector machine. The idea is this is 2D case. The same is for more dimensional spaces. The main idea is to put a hyperplane between input instances, so that hyperplane has the maximal distance between two classes. And we can say that support vector machines are maximum margin classifiers, and because of that feature, they have good generalization ability. The problem is that support vector machines for practical problems can have very large models, and because of that, they are difficult to implement in embedded applications. On the right side of this slide, you can see what is calculated during classification phase. Mostly there are dot products between two vectors. This S is support vector and this X is input instance. Then on the result of dot product, nonlinear mapping is applied, and then we have two more multiplication and one more addition. On previous work, the main idea was to reduce the number of support vectors so that this sum have as few as possible elements. In this work, we present the orthogonal idea. The idea is that inside dot product, we introduce as much zeros as possible, and if we have multiplication between 0 and something, we can skip that multiplication, and in that way we can reduce number of needed parameters for storage, and also we can speed up calculation. That's the main idea of this work. And the first problem is how to produce sparse support vector machines. And in this paper, we presented the simplest solution. The idea is to introduce zeros into input data set. So we take input data set and we try to find the instances with the largest number of attributes which are not zero, and then we in that vector we try to find the attribute which is closest to zero, and we set it to zero. And we go to the whole data set and turn off basically some attributes to zero, and then we use regular support vector machine training. For this implementation, we use standard algorithm implemented in lib-SVM for training. That is first phase, which produce sparse support vector machines. And then we design architecture which can take advantage of sparse support vector machine. We have our previous work, we have RMLC architecture, reconfigurable machine learning classifier, and we made some changes into that architecture to enable it to skip zeros during calculation. The main pipeline is shown here. So the whole sum needed for calculation is split into smaller sums, and then these configurable blocks calculate part of the sum, and that enables more than one input instance to be calculated at the same time. This is coarse-grained pipelining inside the architecture. This is more detailed pictures of our architectures, and the main new module introduced in this architecture compared to previous work is this increment memory, which stores increments which are needed for skipping zero. On the next slide, I will show what's the point of these increments. There is a main configurable module which takes configuration of support vector machine for memory and configure all configurable blocks of the architecture. And here is shown the main idea how zeros can be skipped during calculation. Inside increment memory, there are increments, and there are non-zero values of support vector machines stored in secondary memory. And then when dot product between support vector and input instance is calculated, then every nth attribute of input instance is used for calculations. For example, in these pictures, increments are 2, 4, 3, 1. So only second, sixth, and so on attribute of input instance will be used for calculating dot product, and weights of support vectors will be taken in order from secondary memory. That enables skipping zeros during calculation of dot product, which result in speed up and memory reduction of model. And this slide shows how much speed up we can get compared to RMLC architectures. If frac is a percentage of non-zero values during training, then if there are a lot of attributes in the input instance, then speed up converges to this product. And the potential for speed up is very big, and also the memory footprint of model can be reduced a lot. Then we do some experiments. We use 11 data sets during experiments, mostly standard data sets, which are used in this field. For design of architecture, we use Xilinx Vivado. That's standard Xilinx tool for creating digital IPs. And in experiments, we show that reduction of memory is possible from 3 to 85%, and it is possible to speed up calculation from 117 to 7.92. There are some anomalies which are shown in paper. Something during training, the number of support vectors is increased because all support vectors now have more zeros than previous one. So during training, the number of support vectors is increased, but overall, the number of attributes are decreased a lot. But we cannot determine precisely how much we can reduce the model size. And that's basically what we show that this approach with sparse support vector machines works very good. That's it.
Okay, thank you. Any questions from audience? No? Okay, then I will ask. When you speeding something or reducing memory, usually you must sacrifice something. What is sacrificed in this case? Accuracy of classification?
Yes,
or what?
yes. Accuracy is sacrificed for 1%, 2%. It depends on data set. There are also anomalies in this case also because some data sets are full of noise, and actually when you put some attributes to 0, you can get better results. There is one data set in paper with that characteristic, but overall you lose precision. But that's normal in the embedded system. If you want to implement something in embedded system, you almost always have to lose some precision, because at least you in PC models you use the floating point representation, and embedded system you almost always use fixed point representation. That's at least that's the reason to lose some precision. So that's normal.
Mm-hmm. And can you say, is your solution more or less sensitive to the training set size?
Yes. If training set is so large, then architecture cannot work, because the whole model is basically preloaded into the architecture. So if the size of architecture is can fit into block runs inside FPGA, then architecture can work. But if the model size is so big, then the architecture cannot work. For example, we tried to use the same architecture for convolutional neural networks, and we cannot do it because the model size was too big. For example, there are 100 million parameters in convolutional neural networks, and you cannot store all of them inside the FPGA. But for support vector machines, for decision trees, for multi-layer perceptrons, you can fit the whole model inside FPGAs, and that's not the problem, actually.
Okay, thank you. If there are no more questions, thank you for your presentation.
No problem.
And the third presentation comes from Latvia. Presenter is Vladimir Aristov. And the topic is research of indirect method of measuring the pulse generated output resistance by the step recovery diode.
Good day. I have poor English, so use robots.
So share your screen, okay?
Yes. Yes.
Yeah, and put it at full screen.
Yes. Yeah.
Okay.
Так.
Research of indirect method of measuring the pulse generator output resistance by the step recovery diode. Broadband pulse radar is widely used in such areas as detection and evaluation of human respiration and heartbeat, monitoring the movement of objects both in open areas and behind opaque obstacles, detection of underground objects, detecting living people under the rubble. The key element of the radar is a pulse generator. The operating frequencies are several gigahertz. To excite an antenna at this frequency, pulses are required with very short front durations. A typical value of the pulse front duration is hundreds of picoseconds. To form such pulses we use a step recovery diode, SRD. Using step recovery diode made it possible to form a pulse having the big amplitude and with a short rise time. In the gigahertz frequency band, it is important to match the line impedance. This will increase the potential of the radar. There are also pulses resulting from incomplete matching of the transmitter with the antenna. They are a noise, distorting the picture of reflection from the target. Incomplete matching causes non-informative interfering lines that to appear on a typical radar profile. The slide shows a typical pulse reflected from a metal sheet. Radarogram displays the picture of underground sensing and detection of pipes. A typical circuit with a step recovery diode is shown in this figure. The input pulses are applied from a pulse generator. In the absence of negative input pulses, the diode is forward biased and through it current, so-called pump, flows from the source E. When input pulses are applied, the charge accumulated in the diode dissipates and diode switches very quickly to a high resistance state. A consequence of this is the formation of pulses with a steep front. The generated pulses with a steep front enter to antenna. The probing pulse is formed by antenna. The circuit works with pulses of picoseconds duration in the frequency range. This corresponds to the frequencies of units and tens of gigahertz. Therefore, the circuit in the previous slide is incomplete. The presence of parasitic inductances and capacitors must be taken into account. These include the parasitic elements of mounting the circuit and the diode itself. For a diode, this is the package inductance and the package capacitance. The diode itself is represented in the form of a contact potential of 0:6-0:9 volts and a dynamic resistance. An extended circuit is presented on this slide. To find the output resistance, we have used the method of equivalent generator. For this, entire circuit is represented as equivalent generator and resistance Rg. Load resistance RL is connected in series with them. If there is no output load, there will idle voltage, free running. If there is a load shorted, the short circuit current to flow. Short circuit output resistance is Rg. It is equal voltage over divided by the current ISC. However, as will be shown in the concrete diagrams, in this form the equivalent generator method is not applicable for the analysis of our circuit. This is due to a feature of the step recovery diode. In the absence of an input pulse through the diode flows forward charge pumping current, leading to charge accumulation. Resistance of the diode is low. The appearance of the input pulse causes a reverse current through the diode, leading to dissipation of the accumulated charge. At the end of the last, resistance of the diode rapidly increases and practically all the input voltage is applied to the load. The appearance of the input pulse and the diode switching is accompanied by transients in the circuit. A load resistance, connected in parallel to diode, takes portion dissipation current away, thereby delaying the time of switching. Based on the foregoing, it would be incorrect to find the output resistance of the circuit at an infinitely large resistance load, free running, and its value 0. Short circuit. A consequence of the method of the equivalent generator is the determination of the output resistance by the two values of the load resistance, 1 and 2, and the corresponding output voltages. It is not difficult to verify that in this case, output resistance is determined by the formula shown below slide. Use equation should strive to ensure that the difference between the two load resistors must tend to 0. This will avoid the impact of the change in load on the transition process. How to find the voltage and current in a complex circuit. The circuit has a lot of active and reactive elements. At the input is a voltage pulse, in general of an arbitrary shape. To solve this problem, we use the solution of a system of differential equations. Initially, we have prepared our circuit for applying Kirchhoff's first and second laws to it. It is shown in the figure of this slide. Here the notations appeared. These knots and loops we have assigned to our equivalent circuit. The solution was made in 2 stages. First stage, the accumulation of charge in the diode, the supply of the input pulse, the dissipation of charge, searching diode switching's moment. From low resistance state to a high resistance. Second stage, the processes of the first stage plus the diode switching and the formation of desired voltages and currents. For each stage, based on the first and second laws of Kirchhoff, the system of equations was made. Kirchhoff's first law. According to this law, we have written 2 equations, for nodes 1 and 2. Kirchhoff's second law. According to this law, we have written 4 equations, for loops 1, 1, and 2, 3, 4. We already have 6 equations. The missing 5 equations we have taken as a relationship between the currents and voltages at capacitors and inductors. Due to the complexity and bulkiness of the analytical solution, we resorted to a numerical solution of our system of equations. The result of solving the system is the value of voltages across the load at its various meanings. Efficiency of selected equivalent circuit of generator. Values of elements and calculation procedure is confirmed by practically complete coincidence of the output waveform obtained when the physical experiment and calculation. This slide shows the generator output pulse obtained by A. Calculation, B. Physical experiment, a Tetronix broadband oscilloscope, bandwidth 20 GHz, was used in the experiment. We work in the time domain, therefore, we are interested in the time dependence of the output resistance. The most important is time segment 5 to 12. For this example, nanoseconds when the output pulse is formed. In order to determine the output resistance dependency from nominal values of circuit elements, it is necessary to appoint criterion. Most practical and convenient is to use the average value of the output resistance curve at an interval less susceptible to abrupt changes due to transients, as previously stated. To minimize the influence of the difference of load resistors in calculating the output resistance should decrease this value. Carrying out experimental calculations help determine the boundaries of permissible differences. The calculation results are shown in lower slide. The graph shows that the range of schemes invariance to the difference in loads is 100 microohms. 1 ohm. The lower limit is due to the existence of the rounding noise produced by the computer program. For example, here is shown the curve obtained at load difference of 10 microohms. Using the above procedure to find the output resistance, we have studied the influence of the major circuit elements on it. The nominal value of studied element was changed within reasonable limits. The study results of the main elements are summarized in the graph. The output resistance of the generator of input pulse. There is almost linear direct relationship. Coupling capacitor of input pulse source. At small values the output resistance is high. Coupling capacitor of load. With it increase of the output resistance decreases. The parasitic inductance of diodes wires. Its increase leads to an increase in the total resistance of the diode, and hence the output resistance. Similarly, we can identify the impact of any circuit element. Adjustment of the pulse generator, which allows get the output resistance is close to the characteristic resistance of the line, does not always mean a satisfactory tune-up. Selection of the optimal nominal value of a particular element may cause an increase of rise time of output pulse or decrease its amplitude. Therefore, we should be guided by expediency of adjustments and choose a compromise. As an example, here is a view of the output resistance and an output pulse. They correspond to the good tune-up circuit according to the above described. The main conclusions. 1. A successful extended circuit of pulse shaper on one-step recovery diode is proposed. 2. The model of step recovery diode switching from the state of high conductivity to low is successfully chosen. 3. The created system of differential equations satisfactorily describes the operation of the circuit of the sharpener and allows us to determine its output resistance. 4. There is good agreement between the experimental data and the calculated ones. 5. In the circuit of the pulse generator on the step recovery diode there are several elements, such as output resistance of the input pulse source, parasitic and blocking inductors, separation capacitors. Changing their nominal value is possible to control the value of output resistance of the specified generator. 6. Using the results of calculations for the circuit elements with specific nominal values by means of their adjustment is possible to achieve an acceptable output resistance values close to the characteristic impedance of the transmission line without adversely affecting rise time pulse and the amplitude. Thank you.
Thank you. So does anyone have any questions? Because time limit is exceeded, we going to the next presentation. Okay, thank you.
Thank you.
So the next presenter is from Czech Republic, Michal Prausek, and the topic is energy harvesting plant sensor powered by grow light panel with variable wavelengths.
Okay, hello. I'm Michal Prausek from the Technical University of Ostrava, and today I'm presenting the energy harvesting plant sensor powered by grow light panel with variable wavelength. So it's a major work for my PhD students, and I will present it as well as I can. So, next slide. Yes. So this is the presentation outline. I will start with the introduction, then I will explain the background of the growing light and solar panels. After that, I will show my testing setup and experimental methodology. And in the end of the presentation, I will show the results and major conclusions. So what is the point of this work? So we want to build the energy harvesting sensor, which is equipped by the solar panel, but the solar is not the solar as the sun, but we are using the artificial light. So our artificial light have a different spectral characteristic, and we are using this different spectral wavelengths from the different growing phases of the plants. So we are building the sensors, we are applying to the ground, and we are lighting by the artificial light. We have the major energy harvesting constraints because the sun have some characteristic depending on the light in the night and day, but we have the constant illumination of the solar panel, but we have the different wavelength. So the major point is we want to do some data collection, the data collections about the temperature, soil moisture, etc. And we have to do some data acquisition with some data quality. So we want to increase the data accuracy, sampling rates, etc. This depends majorly on the measuring and sensing period. So we are collecting the data, and in the dynamic data interval, we are sending the data to the network. So it's some kind of the wireless sensor network. In this work, we are focusing only on the parameters of the solar panel. So it means we want to know what is the efficiency of the solar panel during the different illumination by the different wavelengths, the blue, red, and white light. So in general, we have different phases of the growing of the plants. So we are using the different solar radiation during the whole process. So solar radiation is from the 400 to 700 nanometers. and it works differently in several photosynthesis processes. Our LED grow light panel has several LED, red and blue light sources, and also we have the white light source. So where is the problem? The problem is the manufacturers of the solar panels have something like the total solar panel efficiency, which means the efficiency of the sun illumination. So it's not appropriate for our case. For that reason, we want to estimate the precise efficiency for different wavelengths. Of course, we have some spectral characteristic for the different materials, but in general, in the datasheet of the manufacturers, we don't have something like that, because it's some kind of the manufacturer's knowledge. This is our testing setup. We are using 8-channel adjustable light source with the maximum total power of 260 watts. So each channel has the different light spectrum. We can also adjust the total output power from the 0 to the 100%. And we are using several R's here. So we are using the LabVIEW application. We have the light control, spectrometry control, the volt ampere and characteristic measurement, and the settings. We are connected with the light server. Light server drives the adjustable light. This is the LED grow panel. We have two inputs. The first input is the spectrometer. So we know what's the spectrum of the adjustable light. So not just from the setting, but from the measurement. And we have the solar panel, which is in the same distance from the source. And we using the solar panel to drive the electronic load. And by the data acquisition card, we are measuring the input power. So this is our experiment. So we have one selected solar panel. The maximal output power is about 800 milliwatts. And we have two experiments. The first experiment includes the 4 different configurations. We have the two blue configuration and 2 red. And a second experiment includes the 4 configuration of the white light with the different intensities, with the different output power from the 50 watt to meter squared to 200. So this is the result. The first, the quasi-monochromatic light source. It means the blue and the red ones. So we have the first 2. This is the blue one, and the second is the red one. And the result is we measure the total efficiency of the blue source. It's from the 466 nanometers. It's only 6.4%. And for the another blue, it's 9.2%. So it's really low. And in the red spectrum is about the 10.1 and 13.7. So we have the efficiency much below the standard solar efficiency. In the second experiment, we are doing the 4 different intensities, as I said. So we measure the efficiency of the white light with the different intensities. And we get similar results from the 19.8% to 20.8%. So it's close to the solar illumination. It means from the sun. So the white LED is near, the efficiency of the white LED is near to the solar illumination. So what are the conclusions? As I said, this is some kind of the first part of the work. So we want to estimate the efficiency of the solar panel. So we now know the solar panel is heavily spectral dependent. So if we using the LED grow panel, we need to take into account the input wavelength. As I said, the total efficiency in the blue, it's 6.4. To the white is about 20.8. So we have around 1/3 of the total output power if we are using the blue light. So our output is we need to consider the varying solar panel efficiency. And now we are doing the next step of the research, and we try to development the contour algorithm with the input of the different wavelengths. So if we are using this sensor for the different illumination, it must work properly in all conditions. So thank you. That's it, and I'm ready for your questions.
Thank you. Any questions? Okay, then I will ask, because you saved a time. Yeah. So usually when you are talking about artificial light, you have electricity in place. What is the reason to use photovoltaic panels to get energy when you have energy, electricity inside?
Yes, this is a very good question, because the answer is practical. We want to, we have some plants, and it's an agricultural process. So you have to install the LED panels, but in the ground, you have to do a lot of work. So you have to set up the plant, and you want to just pick some sensor. You don't want to do some wiring and stuff. So this is almost practical. So that's the reason.
Okay.
And after harvest, you just pick up the sensor and you can use it again.
Yeah. Okay. And for that reason, I think that special panels should be designed and produced for such purposes, or not? Because they have specific wavelengths, yes. The light and better efficiency would be achieved if the dedicated panels would be used. Yeah?
Yes, but today everything is about the money. So the contractor wants to cheap panel from the market and use it for this purpose.
Okay, yeah. Oh, any questions? No questions, so thank you.
Thank you very much.
So the next presenter is from Sweden, and Vandana Nari, and the topic is performance optimization of accelerated tests.
Hello, everyone.
Hello.
So you can see my slides.
Yes, full screen, please. Okay.
Yeah.
Okay.
So good afternoon, and here I will be presenting my paper on performance optimization of accelerated tests. And this was partly work during my master thesis project. And currently I'm an industrial PhD student at Scania, affiliated with KTH. And for this project, my supervisor is Ludek Kulesa, a professor at Bleking Institution of Technology. So this is the outline of my presentation. I will start with some introduction and background. And then later I will show the problem state. I'll explain a bit about the problem statement. And then I will explain about the proposed model. And then we will have a brief look at the case study and finally end with the conclusions. So nowadays, there is a drastic increase in number of electrical units and electromechanical units in the commercial vehicle. And when it comes to commercial vehicle, the demand of reliability is quite high. And one method of measuring this reliability of a system is by performing accelerated tests on a specific component. And the key principle of the accelerated test is to increase the rate of degradation, by increasing the level of stress levels and the number of frequency of the fluctuation in a controlled manner. And one of the common tests that are performed is accelerated temperature change test. And this test is characterized by 4 parameters, which is the time duration, the stress level range, and the ramp rate of the stress, and the number of cycles performed in the test. These tests are performed using an industrial equipment, which is accelerated temperature change test cabinet, where you can see a basket where you place your component, and the upper slot is the hot chamber where you have the extreme high temperature level, and the lower part is the cold chamber where you have the minimum stress level. And the DUT, the device under test, is known to be at the stable state when the DUT reaches plus or minus 3 to 5 degrees of minimum and maximum temperature respectively during the test. So when we have these results from the accelerated test, we would like to relate these to the real life field results. So this can be done by calculating the acceleration factor. So the acceleration factor is calculated from the test parameter values that we obtain from the test results. And this is calculated using the two common life predicting models, which are Coffin-Manson and Norris-Landsberg model. So even though these tests are quite accelerated, they're still time consuming and very expensive. And at the end, the relevance of these tests are still at question. So the main objectives of this paper is to know what are the stress response distribution in and on the component from the experimental test results and from the simulations. And we would also like to investigate if the simulation tools are credible enough to set the parameter values for an accelerated test. And hoping that this could help us to diminish the test time and test efforts, and also improve the reliability of the tests. And a small note that in this simulation approach, we are using COMSOL multiphysics tool. So nowadays, the test parameters are set for a particular system based on the experience and from standards and guidelines which are developed a few decades ago. And each component is very different from another on the basis of the structure, materials used, and the dynamics and the complexities of the component. So each test parameters for this accelerated test has to be altered to the particular component. So our proposed method, and this alteration of the test parameters can be done using a pre-test before actually performing the laboratory. So instead of doing this experimental in the laboratory because it's time consuming and need a lot of efforts, instead we are proposing to simulate this test in a simulation tool, which is quite easy and also less time consuming. Instead, if you want to perform a pre-test for like 3 cycles, which could be up to 4 hours, simulations can be maybe in an hour or so. So the first step is to analyze the DUT and replicate in the simulation tool, and then define the boundary conditions. And these boundary conditions depend on what type of temperature or accelerated test are you performing. It could be temperature, it could be humidity, it could be vibration, and etc. So once we define the boundaries and have a design for the DUT, and then we set test parameters value, maybe from the standards and the experience that we have. And after setting these test parameters values, we run the simulation and record the results from the DUT. And from the results, we calculate the acceleration factor. Once we calculate the acceleration factor, if this acceleration factor is satisfactory, then we perform our experiment in the lab with the test parameters values that we are satisfied with. If not, then we adjust the test parameters value accordingly, and then we run this simulation again. And from a series of tests that we have performed in the laboratory, we've seen the two main factors that affects these tests are duration and the position. Duration is the time that we give the DUT to reach the certain stress level, and the position is of the position of the DUT affects the area of the exposure that it has to the simulated environment in the cabinet. So now we come to the case study. In this case study, we have used a system which is an aluminum box, which is, as you can see here in the picture, it has like thick outer layers, and it has an engineered plastic material on the bottom, which consists of all the electronical components of the system. And then this plastic material is screwed to the bottom part of the component. And this is how it was done during the test. It was positioned vertically in such a way that the maximum area of the component is exposed to the simulated environment. And the test setup. So in the test environment and the simulation and experimental, we use test parameter values, which are the values that we set before the test. And then after we have done the test, the results that we get, we have an estimated parameter values, which are called EPVs. And then we investigate the deviation between the test parameter values and the estimated test parameters value. And ideally, we would like this deviation to be as small as possible. So we are expecting the test parameter values that we have set to be what we actually get during the test. And for this component, we have maximum temperature as plus 80 degrees and minimum as minus 40. And the dual time, that is the test duration, is 50 minutes at each stress level. And we have run it for 3 cycles. So from the experimental and simulation results, we have got such graphs. So one line here, the blue one is the test, the response from the outer layer of the component, and the green one represents the air inside the component, and the pink one is the response from the plastic layer of the component that I have shown you previously. We have seen that it takes almost 15 to 20 minutes to reach the stable state or the maximum stress level for the outer layer, and then it is much slower ramp rate for reaching the minimum stress level. Even though it reaches the stability, it doesn't reach the complete minimum stress level. And even though we have seen the outer layer of the component reaching the certain levels that we have expected it to, the inside of the component is not as we expected. It's much lesser than what we have seen. And the pink one is as it is from the plastic layer, where it has the electronic components. We want the maximum stress to be faced by that to see the failures that we get by the end of this tests. And when we have replicated this test in the simulations, we have seen similar results, where it takes 15 to 20 minutes to reach. And then it shows that somewhat it has a higher ramp rate than the experiment to reach the minimum stress level as well. And then it shows the similar outline of the response from the air and the plastic inside the component, but not same as the one from the experiments. And we had an added advantage from the simulation results, that we could see exactly how each component inside the system is reacting to this kind of accelerated testings. We see that in this diagram, this is at 50 minutes at the maximum, the hot temperature side. We've seen that the screws face the extreme stress levels, where they're very prone to break after certain cycles. And then here we can see that in the cold chamber as well, the screws are the one which are very crucial part of the system. So this was, we cannot see such kind of results from the lab experiments. Instead, we can also have, this is just an added advantage from the simulations. So now I'm just, this is like a comparative analysis to show you what were the test parameters values and what did we have the estimated parameter values in the experiment that are performed in the laboratory, and experimental parameter values in the simulation results. This is what we have set, and these estimated parameter values are from the air inside the component. That is the green line in both the results. And we see that even though they look similar, the measurements are a bit different. And this is because the component that we've used in the simulations was very less complex, and it was not exactly what we had the component in reality. We have not included all the dynamics in the system, and the component was very less complex. So if we would like to replicate it in full-fledged, we can improve the design that we include in the simulations, and we could actually get the exact results that we get in the results. So some conclusions. From this, we see that the estimated parameter values and the test parameters values, they have huge deviation, and which means that there is an uneven temperature distribution in and on the component during the accelerated temperature change test. And then we see that the dwell time is one of the important factors. That's the test duration that we give the component to reach a certain stress level. It is quite crucial. So that has to be estimated properly during these pre-tests. And then also the results show that the simulation tools can use to be to assess the optimal values for the test parameter values, and also maybe to find a way to speed up these tests in real tests. Thank you.
Okay, thank you. So, how the temperature was measured in your real experiment of every surface?
You mean in the real results? Mm-hmm. Yeah. So we used a temperature sensor that
located in different places.
Yes, we did. And we have insulated in such a way that we had the sensor, and then we had an insulator on top, we made sure that it is not reading the temperature of the cabinet if it is placed on the surface. And
but can that isolator change your real temperature of? Because if you have some isolator on the surface,
it's not that big.
Very small.
So, yeah, just the area that covers the sensor tip, so that it is, and we have also placed it in such a way that it is a bit inside to the material that we are testing, like, you know.
But you know that such modeling using COMSOL or other software is very, let's say, expensive. Yes, I mean time, and for complex systems, it's hard to make a good model. Yeah.
Yeah.
So and when you are simplifying something, you're losing precision. Yeah.
Yes.
So how to find the compromise?
So the thing is, when we do a test in actual laboratory, we just assess with experience that, okay, it might take 50 minutes and it will reach 80 degrees Celsius. But maybe in reality, it is not what we expect. But this simulations, it gives us an idea about how much time it takes to reach that. And it'll also help us to understand if it is reacting to the stress like we wanted it to. And of course, this tool is quite expensive, but when it comes to, I mean, it doesn't, it can be shared. If it is a company or a university, this license could be shared between a lot of people. And the complexity, of course, it is difficult to replicate, but a lot of simulations tools have an option where you can directly take a designed CAD design from the designer and upload it, or upload it to this tool. And you don't have to spend so much time in designing it yourself. In my case, it was a trial, so I had to design it completely by myself, but it can also be an agreement from the supplier whom we get this component, that we get CAD design where we can do a simulation like this.
Yeah, but then computing resources are required, yeah? Big computing resource.
I think for me,
for complex systems.
Yes, of course, it will definitely take, but it's a bit disadvantage that for complex systems it takes time, but also it will, in the laboratory when we want to test an accelerated test, it takes like 4 months, 5 months for a system. So instead of having bad results for this 5 months, it's better to spend a day for just simulations to understand the values and then make it more reliable results. So it's again a trade-off. We can choose what we want in the end.
Yeah, good approach. Yeah.
Thank you.
Okay. Any more questions? No questions. So thank you very much.
Thank you.
Yeah. The next presenter is from Spain. It's our last presentation, and Jose Maria Vicente Samper, and the topic is NFC to BLE communications bridge from flash to continuous monitoring of biological parameters.
Hello, everybody. I'm Jose, and I'm going to present the work NFC to BLE communications bridge from flash to continuous monitoring of biological parameters. The work was developed inside the Neuroengineering Biomedical Research Group at the Miguel Hernández University of Elche. This will be the order for the presentation. In first place, an introduction. Today, there are many activity devices for monitoring biological parameters that use Bluetooth Low Energy to transmit information from the sensors to the user. For example, activity wristbands, chest bands, or smartwatches. For example, Apple Watch allows measuring electrocardiogram, or the Embrace from Empathica can measure electrodermal activity to help control epilepsy. Bluetooth Low Energy maintains a continuous communication. This allows to obtain information from the sensors in live. Consequently, the user can know his current physical status at all times. The continuous communication also allows us managing alarms, and in short, we have a greater control of the information. However, it also has some disadvantages. Despite of the low power consumption of the latest versions of Bluetooth, to maintain a continuous communication for a long time considerably reduce the autonomy of the device. On the other hand, many of these devices need to keep another device close, usually a smartphone, that is connected at all times and the user must carry with it. One option for this monitoring system is the use of the near-field communication system or the near-field communication and communication technology. These are known as NFC biopaths. The NFC only transmits information when the reader approaches it and does not require power consumption for the transfer. The device stores the information in memory and sends it when the user wants through the reader. However, and due to this characteristic, we don't have the benefits of the continuous communication. This work presents a technical electronic solution to convert these flash measuring devices in a continuous monitoring system through an NFC to BLE bridge. The proposed design has two clearly differentiated parts and has overall dimensions of 80 by 70 millimeters. On the upper side, we can see the rigid part with all physical components and the Bluetooth antenna. The bottom part has the NFC antenna and it's made with a flexible material for reader comfort. The flexible part has 84 microns of thickness formed by an internal Cooper layer and covered with polyamide, and it's the 53.75% of the total device surface. The NFC antenna has a rectangular geometry with 60 by 45 millimeters. It's made up of 9 rectangular segments with 0.8 millimeters of width that form 2 complete turns. The antenna has a real inductance of 613.3 nanohenries measured with a vector network analyzer. The resonance frequency of the adapter circuit is 15.58 MHz because the manufacturer of the transceiver recommends between 1 and 5 MHz greater than the operation frequency. And the maximum communication distance of the system is about 10 centimeters. The rigid part has 0.871 millimeters of thickness formed by 2 external and 2 internal copper layers and 2 dielectric sections, one with polyamide and the other one with FR4. On the left side, we can find the power management components, and on the right side are the Bluetooth antenna and the main components of the system. The device integrates a lithium-ion battery of 260 mAh with a size of 35 by 12 by 6 mm. The device also has a micro USB connector as charging interface for using a standard 5 volts charger for electronics. Also has 3 LEDs to show the charge status and another one to indicate when the device is on. The Bluetooth antenna is an inverted F-type. It has been designed to radiate in all directions and does not require any additional components. And it has a gain of 1.26 dBi and a radiation efficiency of 76.75%. In the software implementation, there are 2 main components in the operation of the device: a radio frequency transceiver for NFC communications and a microcontroller with the BLE stack integrated. The change-port period of the application, the management of the memory, and pre-processing operation can be configured by programming in the microcontroller. Here we can see a flowchart of the BLE stack. For the management of the device, we have developed an iOS and Android application. It has a simple interface where the values measured by the sensors are displayed. And also it's possible to navigate in a graph for consulting historical data, make scrolling, zooming, etc. The application also has 2 buttons, one to save snapshots from the graph and the other one to force a sensor measurement. In addition, the app has special features. We can establish a maximum and a minimum limit of the measured values. And the application will sound alarms or will do telephone calls for values out of limit. Also, there are alarms for lost readings, low battery, or Bluetooth disconnection. And finally, it's possible to store the values in a remote MongoDB database to access from remote. In the application section, we can see 2 applications with the NFC to BLE bridge. The first one is a temperature biopatch developed in our laboratory. It's a small NFC device that measures the body temperature of the user every programmable period with an autonomy of more than 1 month. We can use the system in flash mode during the day and convert it into continuous mode with the bridge at night to go to sleep, for example. The other application is to convert the commercial glucose sensor from Apple Laboratories, called Freestyle Libre, in a continuous monitoring system with alarms. In this case, we have incorporated Night Scout integration in our iOS and Android application to manage the values in remote. Finally, as conclusions, a bridge of NFC to BLE allows implementing a high flexibility solution for sensor monitoring system. Also, the possibility of converting a flash sensor to a continuous sensor allows designing more efficient solutions in terms of energy consumption. And 500 bridge units were manufactured for use with the non-invasive Freestyle Libre, and they have been in use for more than 18 months with a great results. Thank you for your attention.
Thank you. As I understood, that bridge should be placed on the next sensor, yeah?
Yes.
If you want to monitor it continuously, yeah?
Yes,
then
if you want... Sorry?
Okay, the question is are these sensors allocated in comfortable places to place your additional board to body?
No, the sensor are comfortable, but in some situation, for example, when you have a son, a little son, and he go to sleep, you need to control his temperature or his glucose values, and you have to go to control him every night. And with this device, you can convert for example, the glucose sensor in a continuous monitoring with alarms, and you can control with your mobile, for example. But it's not uncomfortable.
But it should be fixed next to sensor, yeah?
Yes.
Okay. Any more questions? We don't have questions. Thank you very much for your presentation.
You are welcome.
And we finished almost in time. And I would like to thank you all participants and all viewers on YouTube. And thank you for your presentations. I wish you all the best, and we will meet next time in next conference. Thank you for your attention.